Welcome back to the Deep Dive, your shortcut to getting up to speed on the latest research. Today, we're really digging into something fundamental for, well, trusting anything digital. Deepfakes. We're looking at a super important new paper called OPENFAKE, an open dataset and platform toward large-scale deepfake detection. It's got authors from McGill, Mila, and a few other places. And our mission here, what we really want to figure out, is why our current ways of spotting fakes, the benchmarks we use, are just falling flat against the newest AI generators, and crucially, how this OpenFake project tries to fix that big gap, especially when things get serious, like in politics.
Right. And for anyone needing the quick version, the sort of technical highlights up front, let's do that.
Yeah.
The big picture is the threat has really evolved. These deepfakes coming out of proprietary models, think Imagen 3, GPT Image 1, they're so realistic now that when they tested people, human accuracy for spotting them was down around 49%. Basically just guessing.
49%. Wow. Okay, that's genuinely alarming. It means you literally can't trust your own eyes with these high-end fakes.
Pretty much. So OpenFake tackles this head on. First, with scale and quality. We're talking 3 million real images carefully matched with almost 1,963,000 high-quality synthetic ones. And the key thing, the real innovation in the data itself, is that the fakes come from 18 different state-of-the-art models. And crucially, that includes the big closed-source proprietary ones. It's not just the older face swap stuff anymore.
Okay. So we're moving past just like weird face glitches to much broader, more convincing fake scenes.
Exactly. And the second big piece is the OpenFake arena. This isn't just a static pile of data. It's designed as a crowdsourced kind of adversarial platform. The whole point is to constantly feed it new, tricky fakes that fool the current detectors. So it actually uses that rapid change in AI models, model drift, as a way to keep the benchmark relevant. It learns continuously. And the results really back this up. When they tested the old detectors on these new fakes, they failed badly, often near random chance. But detector models, they specifically used a SWIN v2 transformer trained on this new OpenFake data. They did much better than models trained on older, narrower data sets. It proves that good detection is possible, but only if you train on the right kind of data, broad, up-to-date data.
Okay, let's just pause for a second and really underline why this is such a big deal, why this huge effort was needed. That 49% number we talked about, it's not just a weird stat. It shows deepfakes are seriously fueling misinformation, especially around sensitive times like elections. You hear scholars talking about an infopocalypse on the horizon.
Yeah, and from the tech side, why we're in this situation is actually quite straightforward. Our old defenses, they're just obsolete. Fundamentally, think about the benchmarks everyone used to use, like Face Forensics++ or SolidDF. What were they based on? They were built to detect artifacts from older GAN-based face-swapping tools, things like Deep Face Lab, Face2 Face. These tools left behind pretty obvious clues, low-frequency artifacts, weird blurring at the edges, stuff that older detection algorithms could pick up relatively easily.
Right. They were basically looking for the digital equivalent of bad stitching on a swapped face.
That's a perfect way to put it. But modern diffusion models, transformer models, they don't just stitch things. They generate entire complex, often semantically coherent images, basically from scratch, from noise. The tells are much more subtle now. Maybe inconsistencies in lighting, weird reflections, messed up text in the background, not just warped faces. And another huge problem with those older data sets, their scope was way too narrow. Almost all of them focused on just single faces, like portraits. But real-world misinformation, especially the kind that spreads like wildfire on social media during, say, political campaigns, it's often much richer. You see manipulated signs at protests, fake crowd pictures, fake disaster images, often paired with misleading text, multimodal stuff, static data sets of just faces. They just don't pair a detector for that kind of complex threat. And of course, being static, they became outdated almost the moment they were released because the generator tech moved so incredibly fast.
And it's really interesting, the paper mentions the motivation behind the initial data grab. They specifically say they started scraping content during the run-up to the 2025 Canadian federal election. That means this wasn't just some abstract academic exercise. It was driven by trying to capture actual high-impact political misinformation risks happening in near real time. That gives it a certain immediacy.
Absolutely. And that political context really shaped how they designed OpenFake to overcome those limitations we just discussed. Let's dive into the specifics of the dataset structure. We mentioned the scale 3 million real, nearly 1 million fake images. This huge size supports what they call a rich content scope, moving way beyond just narrow face data to include all sorts of scenes, objects, text, more like what you actually find online.
I want to ask about the real images, though. That sounds tricky. If you want a detector that works in the wild, it needs to handle real-world messiness, like compression, right? How did they make sure their real images were relevant and kept those, real-world artifacts?
Yeah, that's super important for making the detector robust. They started with LAIN 400W. A key point here is that LAIN is mostly pre-pandemic images, so it naturally contains all the messy stuff you find online, images that have been resized, compressed with JPEG multiple times, weird metadata, exactly the kind of noise that trips up models trained only on clean, perfect lab data. But LAIN is massive and varied, so to make it relevant, especially for that political angle, they filtered it. They used a vision language model, specifically Qwen 2.5 Diliol, to go through it. The goal was to keep images that had actual human faces or depicted politically relevant or newsworthy protests, public figures, events, while filtering out things like, say, abstract art or landscapes. This way, the real side of the dataset mirrors the kind of content likely to be faked for misinformation purposes.
Okay, and then the synthetic side. This seems like the biggest leap from past datasets. You said 18 generators. Can you expand a bit on why getting images from proprietary models like Imagen 3 or 4, GPT Image 1, Midjourney 6 or 7, why is that so crucial now?
Oh, it's completely non-negotiable if you want a benchmark that reflects today's reality. Because those models, they're setting the standard for realism right now. Older datasets mostly used open source models, like earlier versions of Stable Diffusion or various scans, which is fine. But if your detector can't spot the fakes coming from the best commercial APIs, the ones generating the most convincing images, then your detector isn't really useful against the highest impact threats. These proprietary models often have better coherence, lighting, understanding of prompts, things the open source world is still catching up on sometimes. Including them ensures the benchmark has truly high realism. It forces the detectors to learn to spot the absolute state-of-the-art fakes.
Right, and for the researchers and engineers listening, actually using these massive datasets can be a pain. Did OpenFake make it easier to access compared to older benchmarks?
Yes. Usability was clearly a big focus. They avoided the old trap of releasing like a multi-terabyte zip archive that's a nightmare to download and set up. Instead, the whole thing is hosted on the Hugging Face hub. And they use the Parquet format, which is designed for streaming. So for ML engineers, this means you can plug it into your training pipelines much more easily, even distributed ones. You don't necessarily need to download everything up front. Plus, they released all the prompts used to generate the fakes. That's huge for transparency and lets other researchers build on or audit their work. Big win.
Okay, let's pivot back to those shocking empirical results. That human study 49% accuracy on Imagen 3. Beyond just being a low number, what does that level of deception really signal about how far these generative models have come?
It signals that the game has changed. The artifacts we used to rely on, the little visual glitches, they're essentially gone, at least to the human eye, in these top-tier models. The jump in quality is just immense. Remember, people could spot fakes from older models like SDV 2.1 pretty of like 88% accuracy. The flaws were obvious. But with Imagen 3, the images are so photorealistic, our brains just seem to default to, this must be real. The threat isn't just noticeable fakes anymore, it's simulated reality that's almost indistinguishable from the real thing.
And the machines didn't fare much better initially, right? This isn't
Yeah.
just our eyes being fooled.
Exactly. When they benchmarked existing state-of-the-art detection models, the results were pretty bad. They picked two main ones, CLIPD 10K plus LIP, which uses contrastive learning, kind of trying to learn general features, and Corvi 2023. Which is known for focusing on frequency artifacts and noise patterns. Both really struggled with the high-quality proprietary fakes. Often, performance was close to random guessing again. CLIPD only got about 46% true positives on Imagen 3 fakes. But Corvi 2023, this was a real shocker. It had a true negative rate, or TNR, of 0.0%.
0% TNR. Hold on. Let's make sure everyone gets that. That means Corvi 2023 labeled every single genuine image it was shown as being a fake.
That's exactly right. Every single real image was classified as synthetic. So if you actually deployed that model, say during an election campaign, it wouldn't just fail to catch the deepfakes, it would actively flag all the real photos and videos as being fake. It creates more noise than it solves.
Wow, that's worse than useless. It's actively harmful.
Completely. And it just hammers home the point. These older benchmarks, and the models trained on them, they learn to spot signatures of old generators. Those signatures just aren't present in the same way in modern fakes. So the models are fundamentally misaligned with the current threat. They don't represent the distribution of fakes we actually face today. Okay, so the threat evolves constantly, making static defenses useless pretty quickly. How do you possibly build a benchmark that lasts? And this is where that OpenFake ARENA comes in, right? The part designed to fight this constant change, this model drift.
Exactly. The arena is, I think, a really clever idea. It's basically a crowdsourced adversarial platform framed as a web game. Anyone can go there, use any image generation tool they want. Could be a commercial API, an open source model, something custom they built. And their goal is to create a fake image that fools the live detector running on the site, which is a SwinV2 model trained on the main OPENFAKE dataset.
So it's like a continuous public red teaming exercise, a game to beat the detector. Precisely that. And here's the feedback loop. If your submitted fake does fool the detector, meaning the detector incorrectly classifies it as real, then that tricky image gets automatically added to the benchmark dataset. So this gamified community effort means the benchmark is constantly being updated with the hardest, most current examples that can fool the existing defenses. It turns model drift from a problem into, well, a source of fresh training data.
Okay, that sounds really promising. So what happened when they actually trained a model on this new, richer, evolving data set? Did it work? Does all this effort lead to detectors that can actually, detect?
Yes, it seems so. The initial results were very strong. The SwinV2 vision transformer they trained on the OpenFake distribution performed exceptionally well when tested within that distribution, meaning when tested on fakes from the same 18 generators it was trained on, they reported near-perfect scores like 0.995 true negative rate, 1.00 true positive rate on many models, and an overall ROC-AUC of 1.00, which basically means it was making almost no mistakes on the data it was familiar with. It proves detection isn't impossible. The main issue really was the inadequate training data before.
A 1.0 ROC-AUC, that's practically perfect separation within that set of known generators. But okay, here's the million-dollar question for anyone building these systems. What about generalization? How did it perform on fakes from generators it had never seen during training? Because that's a real test, right? Can it handle the next new model that comes out?
That's absolutely the critical question. And the results there were also encouraging. The OpenFake trained model showed significantly better transferability to unseen, out-of-distribution OG generators. They specifically tested it against outputs from Grok 2 and Midjourney 6, which weren't in its training set. And it consistently outperformed detectors that had been trained on narrower datasets like GenImage or semi-truths when faced with these new OD fakes. So it really demonstrates that training on that broad, diverse set of generators with all their different styles and artifacts helps the model learn more fundamental, generalizable features of synthetic images, making it more robust against novel threats.
Okay, one last technical detail they address, which is a classic problem, the compression shortcut. We know detectors sometimes cheat by just learning that, say, fake images lack the usual JPEG compression artifacts found in real web images. How did OpenFake prevent that?
Right, that's a common failure mode. They tackled it with data augmentation during training. Essentially, they deliberately roughed up the synthetic images before feeding them to the detector. This involved things like randomly resizing them, applying different levels of JPEG compression, adding other types of noise, basically simulating the journey an image takes when it's shared and reshared online. And this worked really well. Even when they tested the final model on a test set where all the images, real and fake, had been heavily compressed, it still maintained a very high F1 score, 0.992. This confirms the model wasn't just relying on superficial clues about compression. It was forced to learn the deeper fingerprints of the generation process itself. It inoculates the model against being easily fooled by simple pre-processing differences in the real world.
So wrapping this up, the main takeaway from this deep dive seems pretty clear. That gap between AI generation and detection, it's widening fast. Mostly because of these incredibly powerful proprietary models. The old static benchmarks just can't keep up anymore. They're effectively broken, which makes continuous, high-quality, broad data sets like OpenFake not just nice to have, but essential. This work kind of lays out a roadmap for how detection might actually stand a chance.
Exactly. And that leads us to the final thought, the big challenge, really, for everyone listening who works in this space. We've seen compelling evidence here that yes, even very high-quality deepfakes can be detected if you have the right kind of robust training data like OpenFake provides, but a huge chunk of the state-of-the-art generation is happening behind the closed doors of proprietary models. We can see their outputs, but not necessarily how they work internally. So the ongoing race is really about this. How quickly can the research community get hold of, analyze, integrate the outputs from these constantly evolving opaque models into our defenses? How long does the edge provided by OpenFake last before the next generation of image models makes it partially obsolete? And can something like the crowdsourced arena really close that time gap fast enough to matter, especially when the stakes are high? That's the question we're all going to be grappling with tomorrow.